The last thing we're going to do is looking at a specific type of equation where we want to change the polynomials. We know the roots, or at least what form the roots of an original polynomial is. We want to turn it into something else. We want to change what the roots look like. So if we know the roots of a polynomial are alpha, beta, gamma, however many it has, and I want to change it and say, well, okay, well, maybe the roots are alpha, beta, and gamma. What would the polynomial where the roots are 1 on alpha, 1 on beta, 1 on gamma, what would that look like? How do we do it? And it's actually a very simple substitution. What I like to do is I let y equal and make it look like the root, but I place x where the root is basically. So let y equals 1 on x, rearrange it, make x the subject, and I just substitute that into the polynomial. That becomes the new equation. Now, of course, it's not a polynomial equation until I make sure all the powers are whole numbers and then things like that. So, but that's the basic idea. So if it was a constant times alpha, so I wanted 4 alpha, 4 beta, 4 gamma, similar thing. I'd say, okay, I'll let y equal that constant times x, rearrange it, x equals y on k, and I'll substitute that into the polynomial. If I add a constant number to each root, it's the same idea. I could go, okay, well, I'll make y equal x plus, again, substitute in. It doesn't matter, I mean, it's the same technique. If I want to make the roots squared, alpha squared, beta squared, gamma squared, well then I'll let y equal x squared, and I'll substitute in x equals y to the half. So let's look at some examples. Here's a cubic, x cubed plus x plus 2. We're going to form an equation, the reciprocals, 1 on alpha, 1 on beta, 1 on gamma. So let's have a look at that idea. So yep, all right, I'll let y equal 1 on x, x will equal 1 on y. Substitute in. Now I've got an equation, it's not a polynomial though, because I've got the y's on the bottom. So if I multiply everything by y cubed, I'll come up with a polynomial. And so there it is. The solutions to this equation will be the reciprocal of the solutions to the original equation. There is, of course, another way you could do it. I could look at the original equation and say, well, I know that some of the roots 1 at a time, I know some of the roots 2 at a time. I could then work out, oh, well, what's the sum of the roots of 1 on alpha plus 1 on beta and 1 on gamma? I know that would be minus b on a in this new equation. I could do it 2 at a time and work that number out. I could do it 3 at a time, work that number out. So I could do it this way. I just think this is a little bit quicker, doing it this way. Well, it certainly is for this one. And probably would be for this one too. If I'm just going to add 1 to each of the roots. So if I let y equal x plus 1, so I'm going to substitute in y minus 1. And well, technically that is a polynomial, but let's make it look like a polynomial. Expand out, collect like terms. There's my equation. Interesting. So what was the solution to the original equation? Because straight away, without any further ado, I know a solution to this equation. So therefore, the original equation must have a solution of, remember, these are the roots, alpha plus 1, beta plus 1, gamma plus 1. So if 0 is one of those roots plus 1, then the original root must have been. So negative 1 should be a solution to the original. We can test that out. Let's go back to the original.
Oh, it is.
And sub in negative 1. It works?
Yeah.
There you go. Let's try the square one. This has got a little bit more work to do. Because I get a fractional power, you'll notice. And of course, polynomials don't have fractional powers. So when I substitute in, let's tidy that up. I've got 3 on 2 and 1 on 2. Now the only way to get rid of that, I guess, is squaring. Problem is when I square, we're going to go twice the product, that sort of thing. And so I'm still going to have fractional powers. So before I square, what I do is I isolate the terms that have a fractional power on one side, and the things that don't have a fractional power, I'll put on the other side. So on the left-hand side, I've left the fractional powers. I mean, I factorised as well. But the 2 did not have a fractional power. I can put that on the right-hand side. Now I'll square both sides and it'll be okay. Because when I square the right-hand side, I just get 4. When I square the left-hand side, my common factor there of y to the power of a half becomes y, and I have y plus 1 squared. So I will end up now with nice integer powers when I expand the whole thing out. So they will have solutions of alpha squared, beta squared, and gamma squared. So that did have a little bit more work. Would that one have been quicker to work out? Alpha squared plus beta squared plus gamma squared, that would have given me roots 1 at a time. then I could have done 2 at a time. Matter of choice. Oh, reciprocal of the squares. I still use the same technique. It's just now I'm going to substitute in negative a half instead of positive a half. And we get negative powers. Still going to use the same idea. Let's isolate the fractional powers, move everything else to the other side. Before I square both sides, I factorised out the fractional power as negative 3 on 2. So I said, oh, let's multiply both sides by 3 on 2. I suppose, yeah, fair enough. Square both sides, expand, bring it all together. There's my new equation. So if the question now said, find alpha squared plus beta squared plus gamma squared. Oh, look, let's find alpha squared plus beta squared plus gamma squared. Yes, I could have gone to the original equation and worked out it was negative 2. Or, of course, now I could use the equation that we found in C and said, hey, the sum of the roots is minus b on a. That also turns out to be negative 2.